Olá a todos, bem-vindos ao curso de Processamento de Imagens e Visão Computacional do IMPA, com o tema Modelos Generativos Multimodais. E hoje nós vamos falar de como funciona, né, uma rede neural generativa, e essa palestra, na verdade, vai ser mostrar os últimos resultados, né, dos pesquisadores que estão avançando no estado da arte. E são dois trabalhos, né, bem recentes, que foram publicados, né, no SIGGRAPH de 2023, né, e no SVPR, né, e esses trabalhos eles mostram exatamente as técnicas mais efetivas, né, de você controlar o modelo generativo, entendendo como é que é a arquitetura da rede neural, né? Da rede neural generativa, no caso aqui que a gente está estudando, o Stable Diffusion, né? Que é um modelo, né, open source, que a maioria das pessoas que estão fazendo pesquisa nessa área usa, né? Isso vai dar uma boa visão assim, de como o estado da arte avançou desde as últimas coisas que a gente viu, né, tanto teóricas quanto práticas, né? E faz a ponte com essa parte que a gente está vendo, né, dos modelos mais recentes, né, e dos trabalhos que foram avançando no estado da arte nessas áreas, né, de fazer o fine-tuning, fazer diferentes métodos de edição, diferentes métodos de controle, né? Isso aqui, de uma certa maneira, culmina, né, esse processo, e esses papers mostram de maneira muito clara o que tem dentro, né, da rede neural que treina o modelo generativo, né, de uma maneira muito clara e intuitiva, né? Então, exatamente a ideia é essa, né? O que tem dentro de um modelo generativo e como é que você usa, né, aquela maquinária que tem ali para controlar a geração, né, de uma maneira completa, assim, efetiva e intuitiva, né? Então, eu vou apresentar dois trabalhos. O primeiro é esse Plug and Play Diffusion, e depois esse outro que é Attend and Excite, né? E se vocês olharem pelos títulos, né, dá até para entender o que eles fazem, né? E vai ficar muito claro isso na sequência, né? Então, vou começar com o Plug and Play Diffusion, né? Então, como eu falei, esse paper, Plug and Play Diffusion, foi apresentado no CVPR desse ano, né? E é o grupo lá o Michael Geyer, né? Lá de Israel, né? Do Weizmann Institute of Science, né? E você vê aqui que tem, né, uma coisa bastante extensa, né? Porque tem o paper, tem o material suplementar, tem o código, eles têm um demo, né, no Hugging Face, tem um demo no Replicate, né? E fizeram testes com esse titular, né? Que é exatamente para mostrar como é que é efetivo, né? E a ideia é assim, mostrar como eles conseguiram, né, um controle muito bom, né, do processo generativo, coisas que era muito difícil de fazer, mesmo nos trabalhos do estado da arte, né? Então, eu vou mostrar o vídeo, né, e aí depois a gente conversa mais no final da aula.
We present plug-and-play diffusion features for text-driven image-to-image translation. In our work, we enable structure control in text-to-image diffusion models by extending them to image-to-image translation. Given a guidance image and a target prompt as input, we generate an image that fulfills the prompt while retaining the semantic layout of the guidance image. In our approach, we first pose the question of how is semantic layout information internally encoded in diffusion models. And once we understand that, we ask how can we control structure in the generation process. By analyzing the convolutional and self-attention features of the diffusion model, we detect feature maps that are dominated by the semantic layout information of the generated image. Note how semantically corresponding regions across images are encoded similarly. Based on this observation, we control the structure by injecting relevant spatial features and self-attention maps from guidance images generation into the target generation. Here are some example results of our method. In previous work, STEdit proposed to control the layout with the guidance image by noising it to an intermediate time step and sampling from the time step on with the edit prompt. This approach suffers from an inherent trade-off between layout preservation and deviation in low frequencies required by the edit, such as colors. Our method allows both accurate structure preservation and deviation in colors, thus fulfilling the edit. In prompt-to-prompt, they control the generation by freezing the interaction of a generated guidance image with its text when generating an image with a new target text, which allows them to retain the original content. Their method has limited structure preservation, while ours allows fine-grained control over the generated shape and layout, as seen in this example. Their method also requires aligned source and target prompts, while our method works with arbitrary source and target prompts. In Make a Scene, they train a generator from scratch which gets segmentation masks as inputs in addition to the text. This requires large-scale training, while our method leverages a pre-trained model and requires no training. In addition, their final model is limited to segmentation mask guidance and the labels it was trained on, while our method can work on diverse guidance images and arbitrary prompts. In our work, we consider Stable Diffusion as our text-to-image generator. It gets as input a Gaussian noise and a text prompt, and is based on a unit architecture, where each layer consists of a resonant block, a self-attention module, and a cross-attention module for injecting the prompt. We start by sampling images and extracting feature maps from the generation process. For real images, we use DDIM inversion to get the initial noise. We do this on a set of multiple images that share semantic parts. We then group the feature maps by their layer and the time step, and perform a principal component analysis on each group, which allows us to reason about the visual properties dominating the higher-dimensional features. We analyze the features on different image sets, and visualize the three leading PCA components as RGB channels. We observe that a specific layer in the decoder of the UNet is highly dominated by the semantic layout information. As can be seen, for each image set, similar semantic parts share the same colors, meaning that their activations are similar across the images in the set. Recall that the decoder block of the diffusion model consists of resonant, self-attention, and cross-attention blocks. Particularly, the self-attention block computes the similarity between the spatial query and key features. The concept of self-attention is thus closely related to self-similarity, which has been shown to serve as an excellent structure descriptor in both classic and modern works. To visualize the self-attention of a generated image, we apply PCA on the self-attention matrix and visualize the three leading components as RGB channels. As can be seen, the self-attention matrix aligns with the structure of the generated image in all the decoder resolutions. Based on our observations, we now turn to controlling the structure in the generation process. Given a guidance image and a text prompt as input, we first invert the guidance image to an initial noise using DDIM inversion, which is then progressively denoised using DDIM sampling. During this process, we extract the coarse spatial features and the self-attention maps from the decoder layers of the diffusion model. We then initiate the target generation process using the original inverted noise and the target text prompt. To preserve the guidance structure, we inject the extracted features and the self-attention maps to the target generation. Here are some example results of our method. It can work with minimalistic guidance images. It can handle multiple objects. We can also be creative in translating between diverse object classes while maintaining the guidance structure. We qualitatively ablate our key design choices. As can be seen, only injecting the coarse spatial features is insufficient for preserving the structure, while injecting spatial features in higher resolution layers results in appearance leakage from the guidance image. On the other hand, only injecting self-attention maps does not preserve the structure as it lacks the initialization of the semantic layout in the coarse decoder features. Our final method exhibits fidelity both to the guidance structure and to the target prompt. Our method achieves high-quality results of text-guided image translation in diverse image domains and prompts. Since there is no existing benchmark for such diverse settings, we created two new datasets of text-image pairs. Wild TI2I, which consists of 148 pairs and contains both real and generated images, and ImageNet R TI2I, which contains high-quality images collected from ImageNet R accompanied by prompts created using ImageNet R's renditions and object classes, resulting in 150 pairs. To numerically evaluate the results, we use two complementary metrics. To measure the extent of structure preservation, we use dyno key self-similarity distance between the guidance and generated images. To quantify the target prompt fidelity, we measure clip cosine similarity between the target prompt and the generated image. As can be seen in the evaluation results on the ImageNetR TI2I benchmark, our method achieves both high preservation of structure and high fidelity to the target text prompt, while other methods either struggle in structure preservation or in complying with the target text prompt. The same observations hold when evaluating on wild TI2I and generated ImageNetR TI2I benchmarks. Thank you for your attention and visit our website for more results and code.
Bem, então agora eu vou passar para o segundo trabalho, que é esse Attended Site, né, que de uma certa maneira complementa esse primeiro trabalho, né. A ideia do Attended Site é um trabalho também de Israel, né, do grupo lá do Dani Cohen-Or, né, que foi publicado no SIGGRAPH desse ano, né. E a ideia é que você consiga usar, né, informação semântica, né, para guiar o processo generativo de difusão, né, usando a técnica de texto para imagem, né. Então, você vai ter a semântica no texto e você quer que essa semântica do texto seja fielmente seguida, né, condicionando o modelo generativo. E aqui o título já fica bem claro, né, que ele vai usar exatamente os mecanismos de atenção e fazer uma excitação nesse mecanismo de atenção para que a semântica seja respeitada, né? Então, eu vou deixar os autores apresentarem, passar agora para o vídeo deles.
Attention-based semantic guidance for text-to-image diffusion models. With the advancements of language-guided image generation, given simple text prompts like a photo of a dog or a photo of a cat, we're able to generate realistic, diverse imagery. Yet, when we try to generate more complex scenes containing two subjects, such as a cat and a dog, these models often fall short in achieving the desired result. We analyze the state-of-the-art, publicly available Stable Diffusion model, and pinpoint two semantic issues of existing models. First, we observe the existence of catastrophic neglect, where one or more subjects is not generated by the model, such as the green bowl in the provided example. Second, we analyze incorrect attribute bindings, where an attribute such as a color is incorrectly matched to its subject. Here, the bench is incorrectly colored yellow instead of brown. In an attempt to mitigate these issues, we introduce Attended Excite. Our goal is to shift the latent code at each time step of the denoising process to better consider the semantic information given in the text prompt. In a sense, we want to attend to all subjects in the driving prompt. Let's start by understanding how text-guided generation works in the standard Stable Diffusion process. Here, at each time step, we inject the text embedding of the given prompt into the UNet of the trained diffusion model in order to guide the model in generating an image described by the text. However, nothing explicitly encourages all semantic information to be attended to by the model. Here, for example, Stable Diffusion ignored the crown present in the text. The text is incorporated via the cross-attention mechanism, which takes a representation of the latent, which we'll call Q, and a representation of the text, which we'll call K, and calculates an attention map between the image and the text. Here, each column of the attention map represents a single token of the text. We can take this column and reshape it to be P by P, and visualize the cross-attention map for the specific token. That is, we get a spatial map representing each token in the text. The attention values in this column indicate how much this token n is present in each of the image patches ij. Here we visualize the cross-attention maps obtained for each token after the regular Stable Diffusion process. And we can see that in this case, the crown did not attain a strong activation. Intuitively, for a subject to be generated, it should have a high activation value in at least one image patch. Here, we see the cross-attention maps obtained with our Attended Excite approach, and we can see that both the line and the crown obtain high activations. Following this intuition, for each subject token, we define a loss quantifying the existence of at least one patch with a high activation value. Given the two subject tokens to consider, here a line and a crown, the loss for each subject is defined using the highest activation in the subject's attention map. If the subject has a high activation value, this loss should be low, like for the line token. Conversely, if all image patches attain a low value, this loss should be high. We then take this worst case as our overall loss for the current time step. Intuitively, we try to strengthen the activations of the most neglected token. Now, we want to update the latent so that it better considers the most neglected token. Therefore, we'll shift the latent according to the gradient of our loss. This process is repeated during the early denoising time step, where the spatial location of each object is determined. And here are some results where we compare a tendentic site to Stable Diffusion and two other baselines that also seek to mitigate similar semantic issues. Here, for the prompt a cat and a dog, Stable Diffusion often generates two cats instead of a cat and a dog. When looking at composable diffusion, the results often merges the two subjects into a single object, rather than generating each individually. And analyzing the results of structured diffusion, the results often resemble those of Stable Diffusion and fall short of correcting the issue of neglect. On the other hand, when using a tendentic site, shown to the right, we're able to generate nice images of a cat and a dog. Here are some results for the prompt a red bench and a yellow clock. Observe that when using Stable Diffusion, we're not able to get correct attribute bindings. For example, the bench is often yellow instead of red, and when a clock is generated, it is red instead of yellow. On the other hand, when using a tendentic site, we're able to generate images that correctly contain a red bench and a yellow clock. We can also consider more challenging prompts that may contain different settings, such as a Picasso painting in the garden. And notice how a tendentic site, we correctly place the paintings in the garden, whereas Stable Diffusion fails to do so. We also consider prompts that contain 3 or more subjects with interactions between them. Here, Stable Diffusion can generate a cat with a meadow in the background, but fails to generate the butterfly. In our images to the right, we see that both the cat and the butterfly are present in a meadow, and it appears as if the cat is chasing the butterfly, which aligns nicely with the given prompt. Thanks for watching. Find out more in the paper.
Ok, então vou parar a gravação aqui.